How's it going, Connor? Hey, Zach, how's it going?
All right, how are you doing?
Doing all right, thanks. All right. All right, it's 12:30. I know people are driving, driving from wherever they are, doing move-in and stuff like that. So we're just gonna get started. Other people will filter in. Some people might not. We'll just do what we're doing. All right. Lord, thank you for bringing us together this afternoon. Thank you for giving us the opportunity to come back to campus next week, to move in this week, to move forward with the semester with a sense of hopefully excitement and um, Lord, just keep us focused, help us to finish through the whole semester strong. In your name we pray. Amen. All right. So, okay. And that for right now. Looks like we've got three of you are here and one of you is not. Interesting. Okay, cool. Well, thanks for being honest. Appreciate it. All right. Excuse me. So, what are we doing today? Right? What are we doing today? Today, we are actually switching topics, right? So, we had our homework due, right? So, let's pull this up because why would we want that to actually do anything? All right, so let's look at this. So, what was confusing about last class? Distance struggling. I'm imagining I'm struggling to understand the equations, right? When we're talking about projectile motion or kinematics in general, right? Um, the kinematic equation sheet is our friend, right? It's our friend. It's going to help us, but only in cases when we have constant accelerations, right? Uniform acceleration. Okay. Distance. I guess people were struggling to get the distance in um, in the experiment that we ran. I'm guessing. Um, so that equation sheet that I've given you, right? The standard forms of the equation are on the top. All of the other sections of it are just, okay, I'm interested in finding this value and I was given some other things, right? So I can solve for it. More than likely, when we do kinematic problems, especially for projectile motion, right? More than likely, what we're going to have to do is chain a bunch of these equations together, typically two, right? Because think of it this way, right? If you're plotting something on a graph, right? If you're making a graph, you have an x, y coordinate, right? You can plot a line that goes through 0, 0, then it goes to 1, 1, 2, 2, right? That's telling you where it is on the x and where it is in the y. We're breaking down projectile motion in the same way. We're breaking down the path of our object in x and y coordinates, except that there is a third coordinate, right? There's time. It takes time to reach that xy coordinate. And in certain situations, we know what that time is, right? We know something. We want to know in 5 seconds, where is this projectile going to be, right? So you would solve the distance in the x direction in 5 seconds and then in the y direction in 5 seconds. Or you know that at a certain x distance, say the entire travel, right? Like when we had the projectile on the cliff, right? You knew that at a certain distance it was going to hit the ground and it was going to be at a given y distance. Well, you can figure out how long it takes to get that y distance, right? When it hits the ground, because we know when that happens. And then you can use that time to see, well, how far did I get in the x direction when y is 0, right? So it's just chaining together a bunch of all of our equations, right? If so, we're going to switch today, right? We're going to switch from kinematics to kinetics today, and we'll talk about what that means in a minute. But for right now, right? If you still think that you still find that you're struggling with the idea of kinematics, please come to office hours, right? And we can talk about it. We can try to walk through everything. If it's the fact that we do a lot of things symbolically instead of plugging in numbers, you just need to practice. We need to practice that. That is really important. I know you guys don't believe me, right? Because none of the students ever believe me when I say it. But being able to work something symbolically, especially on the homework where you get infinite chances to do it, if you do it symbolically at first and then your numbers change, it's a lot easier to change the last step by plugging in the numbers than it is to redo your entire problem because you started with numbers in it at the beginning and you don't know where everything goes. So it's really a time saver. Do you guys have any other questions on kinematics really right now that I didn't get to in here? Before I forget, Zach brought it up to me. The due date in McGraw-Hill was not right for the Learn Smart for chapter 13, I believe, whichever the third one is in the list. So I've opened it up so you guys have until midnight tonight to finish it if you didn't finish it before the previous deadline. Okay, so make sure you get that done if you didn't. Okay. Is there anything else? You guys doing all right?
We'll be able to go over homework in like office hours.
That's fine. That's a perfect time to go over it.
Okay. Or even like the last one, I guess.
Okay. Yeah. I've office hours right after class, Zach. So if you're free from 3 to 5, I'll be sitting in a Zoom meeting waiting for people to come on in. So we can do that.
Okay. I might have to do Friday maybe.
Okay.
Yeah.
Yeah. Every day except for Thursday from, well, every day except Monday and Thursday from 3 to 5, and then Mondays mornings 9 to 11 a.m. Our office hours, right? So you don't need an appointment. You can just come on in. If those times don't work for you, but you think some other time might, we can see if that fits with my schedule and we can do a private Zoom meeting, right? But you got to check with me to see if that works. Right? But I'm always there during the times I say I'm going to be. Just sitting there in my office with my camera off and my mic on mute, waiting for people to join. Right? That's it. All right, so we've got some things due now, right? And this is going to take us out for the next couple of weeks, right? This is going to carry us through topic 2, our topic 2 assignments here. The VOT product plan. We'll talk a little bit about this in a second, but this is a vertical axis wind turbine product plan. And this is going to feed directly into our term project, right? Later. So we're going to cover this in a few minutes. Then we've got homework 2 and 2 more Learn Smarts, chapter 9 and chapter 14. Those are due on the 4th. Okay, so you've got a couple weeks. We've got our VOT product plan due this Sunday. So just be aware. Let's do these things. These dates are also in LoudCloud, right? So what is the VOT product plan, right? What is it? Great question. So I pulled this directly from LoudCloud, but let's go over it together. Okay. So the VOT plan, right? Product planning is the process used by industry to move a product from the product idea through the creation and introduction of the product to the marketplace. In a typical product plan, the following must be defined. Who is the market, right? So where are you trying to bring your product? What is the size of the market? How big is the population you're trying to bring this to, right? What is the value proposition? How is not just financially, like not just what's your return on investment, but how do you also improve the surrounding communities, right? So you're going to design a vertical axis wind turbine or a VOT to produce electricity for a small village that's off the grid. Electricity will be used to operate a clean water project for a population in desperate need of clean drinking water in close proximity to their homes. You need to complete the assignment under the following assumptions. First, that the village that you are servicing has a population of roughly 200 people, each of whom need a minimum of a half gallon of drinking water per day. So you can figure out how much water you need to produce a day, right? The assignment requires you to follow the industry standard of submitting a product plan, but you also need to integrate a component and compare the impact of human lives. This is your value proposition, right? What is the impact of your VOT on human lives versus the cost of the product? Discussing how this relates to Christian worldview of caring and serving for others. Include the following: a clear, concise, and logical mission statement and a vision statement that discusses where you are going and how you are going to get there, right? So your mission statement says, this is my mission, right? This is the mission of my company. Imagine, all right, so how do you approach this, right? We want to imagine that each of you is doing this individually, and we want to imagine that you are pitching your idea for your vertical axis wind turbine and to investors, right? So people need to know, what is your company all about? What is your mission? What is it that you intend to do, right? And then your vision statement. How do you intend to get there, right? How do you intend to get there? You want to identify the market and discuss regional deployment, pros and cons of the identified region, the need analysis in the region that you choose, and the logical decision making that you go through. So basically, you need to figure out where in the world you want to put your wind turbine. Now, there are certain variables that are important for a wind turbine to work, right? So you don't want to put them someplace. You don't want to pick a place that's going to make it harder for your wind turbine to produce energy, right? Because remember, the wind turbine is being used to create energy, and the energy is used to run a pump, and the pump is going to pump the water into your filtration system, right? That's how the system works. So, what do you guys think would be the most important thing that you would want to consider if you're trying to deploy a vertical axis wind turbine somewhere? What is the one thing that you absolutely need? Otherwise, it will not work. What is it? What's the one thing that is essential for the operation of a vertical axis wind? Anybody? It's in the name.
Wind.
Wind. You don't have wind, you're not gonna be able to get any energy out of this, right? So please make sure you pick a region that has wind, right? That has high winds, high average winds. The higher the better, right? But the other side of this is you need a place that actually needs the clean water too, right? So when you're doing a lot of this research is focused on regional deployment, right? Where are you going to put it, and why is that a good place for you to put it, right? What decisions did you make? What criteria did you use in deciding that this was a good place to put it? We want to identify a minimum of 3 possible suitable nonprofits for you to partnership with, right? So, you say, hey, I noticed that X, Y, and Z, all their mission all aligns with what we're trying to do here, and I think they would be good partners for these reasons, right? So pick 3 nonprofits that are suitable, right, and detail how you can partner with them in making this a reality. You should also highlight any complementary areas. So maybe it's not exactly the same, but you guys complement each other in a specific way. And you need to incorporate an analysis of Christian worldview in the context of how the socioeconomic factors affect the surrounding community. So how are you bettering the community? How are you serving the community with your vertical axis wind turbine? Okay. You guys have any questions so far on this? Not yet. Okay. So that's the assignment, right? So you need to create this document, and you do it all individually, right? As I said, this is going to be a recurring theme throughout the semester. We're going to have VAUT individual assignments, and eventually you guys are all going to get together and decide in your CLC groups what you want your design and stuff to look like. The overall goal here is that you guys are going to actually prototype a vertical axis wind turbine. We're going to 3D print the blades, and then we're going to test it. We have a way of testing it with the wind tunnel. I'm hoping that it will be up and running by that time. If it's not, we'll figure something else out. But as of right now, we will say that we'll be using the wind tunnel to test these, right? And you'll get more about those criteria when you need them. But for right now, focus on this stuff. All this information's in LoudCloud. Please read through it and ask any questions if you have any. Okay. So like I said, today we're going to start up with topic 2, right? Kinetics of particles overview. And we'll jump into linear momentum of a particle. We'll talk about free body diagrams and kinetic diagrams. No, not that KD for all of you who are gamer savvy. And normal and tangential coordinates. We talked a little bit about normal tangential coordinates last class, right? So we're going to dive a little deeper into that here, right? So what are the objectives, right? What are the objectives? We want to be able to solve kinetic problems involving particles by applying Newton's second law of motion. We want to derive impulse and momentum from Newton's second law, derive work and energy from Newton's second law, solve kinetic problems involving particles, and solve using work energy and solve them using impulse and momentum, right? It sounds like a lot. it's not as bad as it seems, I don't think, right? So we're going to focus on this guy for a while. Remember, we're talking about particles, not rigid bodies, so it's not as complicated. Like this will get a little bit more complicated when we get there, but for right now, we're just talking about particles, right? So something that we're defining as a single point in space. So Newton's second law is that the sum of my forces is equal to my mass times my acceleration. In this case, right, what I will sometimes refer to this portion here as, this is known as my inertial vector, or sometimes my inertial term. Sometimes I will call it that. And we'll see what I mean in a second, right? So the resultant force acting on a particle, if it is non-zero, the particle will have an acceleration proportional to the magnitude of the resultant and the direction of the resultant. So, okay, so if I'm summing all of my forces up and they equal to zero, right, that's statics. Sum of my forces is equal to zero, right? And if my forces, the sum of my forces equals zero, then everything's in equilibrium, right? We're not accelerating, and that's great. We know how to handle that because Dr. Collin taught us how to do that. What happens when we are accelerating, right? All of our forces aren't balanced. Well, that equals my mass times the acceleration of the particle, okay? Oh, it's also Newton's second law, right? It must be expressed with respect to a Newtonian or an inertial frame of reference. We talked a little bit about frame of reference. What does this mean? This means that we need to talk about it from a fixed reference frame. We're not going to have any of those crazy things that we were talking about where we have rotating frames or anything like that. We'll learn how to deal with that later. But for right now, if you draw this, right? If I draw this on the paper, right? X, Y. That was awful. I'm going to draw that again, but on the other side of the screen where the pen works better. I'm going to blame it on the pen. That's totally the pen, guys. Totally the pen. All right. This is my origin. Everything's going to be measured from this coordinate system, right? It's all going to be X, Y. It's all going to be fixed in space. Everything gets measured from here. So if I have a particle here that we'll call P, look, that's my vector, right? This is R, right? And it has X and a Y coordinate. Right? We're going to talk about it in 3 dimensions for a little bit, but we're going to come back to 2-dimensional problems until the end of the semester when we explicitly go through how to do a 3D problem. For now, right? For now. Must be important because it got bigger, right? Either that or it ate a mushroom. This is a really important equation. It's a really important equation. It's where we're going to live for a while, at least the next couple classes. So what is kinetics compared to kinematics, right? We talked about kinematics. Kinematics refers to the path along, like the geometry of motion, right? How do I define the trajectory of something? That's kinematics. Kinetics is how do I talk about the forces that created that motion, right? How do I talk about the forces that created that motion? How do I figure out how much force it takes to move something? So in order to talk about kinetics of particles, we need to be able to analyze, well, so why do we want to talk about kinetics, right? Well, if we can analyze all of the forces acting on a race car, then we can design a good track, right? We can know how much force the road needs to be able to absorb. We can know how much force interacts between those two objects, right? If we have a centrifuge and it reaches high velocities, we need to make sure that the arm doesn't break, right? We need to make sure that the force on the arm doesn't break. So I don't know if you guys have ever played with a centrifuge. I did way back in the day when I took Chem 1 in college. And we actually, in our lab, we had a vial break in the centrifuge. It is not a pleasant sound at all. And it is even worse to have to clean that out. So we really want to make sure that things don't break in our centrifuge. So what about, you said we're going to talk about forces. Why are we talking about momentum? Well, turns out that yes, Newton's second law is that the sum of the forces is equal to mass times acceleration. That's not how Newton wrote it originally. It's not. He wrote it as mv dot. Wrote it as mv dot. Okay. So he actually came up with his second law of motion and he derived it from the principle of momentum, right? And so again, we're going to go through the derivation here, okay? This is more for your information. I'm not so concerned that you guys know how to derive this, right? This is background info. I'm concerned with you guys figuring out how to apply it, right? So if we write this, right, this is just another way of writing, oh, shoot. It's not another way of writing system of units, guys, sorry. That's just MA, right? That's all that is. The derivative of the velocity is the acceleration. But hopefully we recall from physics 1 that momentum is mass times velocity, right? So if momentum is mass times velocity, right, and mass is constant, at least it should be, we consider it to be, right? Then I can pull that derivative out, right? Because we went over derivatives, and one of the properties is that that you can pull a constant out, but I can also put a constant back in if I want. It works in reverse. So this is just the sum of my forces is the change in my linear or my translational momentum with respect to time. Okay. So that seems weird to think about it that way, right? But it goes to show you that if you know what the momentum is and you understand how momentum changes with time, then you also understand how the forces act on that object. Linear momentum can be conserved, right? If the resultant force on a particle is 0, the linear momentum of a particle remains constant, right? So we often say that momentum is conserved, right? The amount of momentum I have at the start is the amount of momentum I have at the end, right? We often say that. We'll talk more about that when we actually dive into momentum, right? So, okay, so this is where the sum of the forces comes from, right? This is also the part of the semester where I remind you that units are important, right? So it's been a couple weeks since you've heard me talk to you about how units are important. So I just wanted to remind you, they're still important, right? Make sure that you're taking care of your units. Again, I don't care if you use SI or English or customary, whatever you want to call it. Just be consistent, right? I think we can all agree that SI is superior in many ways. We would all agree on that. And if you don't, you can @ me in the comments. It's fine. Okay. All right. So what about equations of motion? This is where we're tying this back now to Newton's second law. So, all right. So Newton's second law, the sum of the forces is equal to mass times acceleration, which is also just the time derivative of our momentum. Okay. So we can use scalar component equations. We'll call them rectangular components to describe Newton's second law, right? And so this is drawn in 3D, right? This is drawn in 3D. So we've got our ijk vectors again, right? So we've got our unit vectors. They're all centered here on the origin, right? So we can see right here, right? That's my origin. And then I've got ij and k going around over here. Oh, didn't want to do that. All over the place. No, of course that's not gonna, that's fine. We got it. So I've got I, J, and K here, right? X, Y, and Z. I goes with X, J goes with Y, K goes with Z. So what this is saying is that if I have some vector R, right, I can write that in terms of an X position, a Y position, and a Z position, right? So I could say, look, here's my X position, right? And I've got this much in the Y, right? And then I've got some Z position, right? Which is supposed to be going in and out of the board. I realize that it's horribly drawn and, you know, dishonored my ancestors and all that. I apologize. But I think you get the point, right? If you have a point in space, you can draw a vector there and it has an X position, a Y position, and a Z position, right? Okay. So we can do the same thing for a force, right? We can draw our force vectors in 3D or 2D, but we can break them down into components like X, Y, and Z, right? The same way that we do our positions. And so if you have a force vector, well, you can break that down into the sum of the forces in the X direction is equal to mass times my acceleration in the X direction. And the sum of my forces in the Y is equal to my mass times the acceleration in the Y. And the sum of my forces in the Z is my mass times my acceleration in the Z. Right? So, right, we can break down all of our forces into directional components, right? And the line below that, right, that's just X double dot, Y double dot, and Z double dot. That's saying, okay, the position, the second derivative of my X position, the second derivative of my Y, and the second derivative of my Z position, right? Because the second derivative of position is acceleration. All right. Is everybody okay with this so far? Ish? They're okay-ish? So what does this mean? For 3D, it's a lot more complicated. When we generalize it to 2 dimensions, right? Again, all right. So for dynamic equilibrium, right? So just because the sum of your forces, so this is different than the sum of my forces is equal to 0. And this is how. If the sum of your forces minus your inertial term is equal to 0, then you have dynamic equilibrium. It is a slight difference, but it is a difference nonetheless. This is saying what? Well, if you think about this, right? We talk about inertia, right? The concept of inertia. What is inertia? Inertia is the amount of force, right, that I have to overcome, right, to get something to start moving. Right? So if I have a box, right, that's 100 pounds, and I want to move it, I have to push with a certain amount of force to move it, right? If I'm pushing and nothing's happening, I haven't exceeded the force limit for it, right? If I want to pick something up off the ground, right, I need to exert a certain amount of force in order to do so, right? That bare minimum amount of force that you need to get something to move, that is the inertial term, and that is your inertial vector. So if the sum of your forces is equal to that, you won't move, right? If it's more than that, then you will move, right? If it's less than that, you still won't move. Right? So we're trying to break that. We often talk about this when we're talking about friction, right? We're trying to break friction. All right, so that's really it, right? With the inclusion of the inertial vector, the system of forces acting on the particle is equivalent to 0. Right? We don't really need to go through all this. Basically, if the sum of your forces minus mass times acceleration is equal to 0, then you're in dynamic equilibrium. That's what we need to know. Okay. All right. You guys have any questions so far? Right. The biggest thing that I want you to take away from the last few slides is the fact that you can break things down into X and Y components, specifically for 2 dimensions, right? If I was to draw something in 2 dimensions like this, right? And I've got X and Y, right? And I know that I have some point out here and I'm applying on this particle, I'm applying a force here, right? This is my force, right? Well, how much force do I have? Well, I mean, couldn't you just talk about this in terms of components of a right triangle, right? Where you have your force in the X direction and your force in the Y direction? Because that's the whole idea of breaking things down into components, right? And in order to do that, you need this angle, right? But what is that angle? What is that? How do we figure that out? Well, honestly, the force acts in the same direction as the position vector, right? So if you know where this is in space, right? If say, for example, we said that this was at 1, 1, right? This angle would be what? It would be 45 degrees. How do I know that? Well, this gives me my X and my Y coordinate in space. This would make a line from the origin. That's that dashed line. And that angle would also be theta, right? It's just along the same path. Okay. So we can use trig, right? We can use trig to figure out what f cosine or f cosine theta is f of x, and f sine theta in this case is f of y, right? If we wanted to add these back together and get the total force, right? Well, we know that the force squared is equal, right? We would just use Pythagorean theorem, right? Just use Pythagorean theorem. So again, the trig is going to be around, right? We're going to do some vector stuff. But before we even get into that, I want to talk about free body diagrams, right? So the way that I want you guys to approach problems in this class, you always have to make sure that you have a free body and a kinetic diagram. What is a free body and kinetic diagram? Well, free body diagram, I'm pretty sure you guys are familiar with from physics, right? And there's some rules here that we have to follow when we're talking about a free body diagram. First, we want to isolate the body of interest, right? So if we were going to draw a free body diagram for this block on this inclined plane, we need to remove the block from the inclined plane. What do I mean by that? What do I mean by that? Well, I mean, you have to take it off the plane, right? You gotta take it off the plane. So there's my block, right? Okay. Then I'm going to draw my coordinates, my axis. In this case, I have chosen that X will be along the incline and Y will be perpendicular to the incline, right? Can you choose other coordinates? Sure, you can choose whatever you want. It's fine. We talked about this a little bit. Certain coordinate systems make things easier and certain things make things harder. I recommend that you always pick it along the incline, right? Always. Then we're going to add in our applied forces. These are things like the weight and how much we're pulling by, right? Notice the weight always points straight down. It doesn't go along the coordinate axes, right? It goes straight down, right? Back towards the ground. Okay. Then we need to replace the supports with forces. That means we need our normal force, right? If we're in contact with the ground will be pushing back, right? This goes back to statics, right? This goes back to statics. If you have something connected to something else, there's a force that's holding it in place, right? And we also have friction in this case, right? Because I mean, that just exists in basically every system. Once we have all that stuff done, we're going to draw our appropriate dimensions. So in this case, I need to draw my 25-degree angle. Okay? And that's my free body diagram. The thing about free body diagrams and kinetic diagrams is that when you put them together, they give you a graphical representation of your equations of motion. So they'll give you a graphical representation of the sum of the forces is equal to mass times acceleration. So if you have a good free body diagram and kinetic diagram, you should be able to draw you should be able to get your equations, right? All right, so everybody okay with the rules for free body diagrams? You guys feel good about free body diagrams before I even started talking about it? Have you guys seen free body diagrams before? I'd be very shocked if you hadn't. And also very concerned. I have to march right up to Dr. Kong's office and ask him what's going on. All right, cool. Oh, yeah, so here we go. So what is a kinetic diagram, right? Kinetic diagram starts the same sort of way, right? We put our inertial terms, we're going to put our inertial terms on our kinetic diagram, right? So how do we do this? Well, we isolate the body first, right? You have to isolate the body. Then you're going to draw the mass times acceleration of the particle. If you don't know which, so a general rule of thumb is you should always pick things positive, right? Even if you don't, so if you don't know which way something's moving for sure, pick it positive, right? Pick MA as positive. If you do know what way something is moving, then pick it the way it's moving. But you'll see more often than not, I default to positive. Because here's the thing, your math's going to check it, right? So if it comes out negative, you know you have to flip the direction, right? That's all that means. When I say draw mass times acceleration, I mean it, right? You just draw an arrow in the direction, right? In the x direction as MAX and the y direction as MAY. That's it. That's the whole thing. And notice they are set equal to one another. Why are they set equal to one another? Because what you have just created with a picture is that the sum of the forces is equal to mass times acceleration. They're vector quantities, right? They're vectors. Or sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction is the mass times the acceleration in the y direction. So when we go to analyze this, right, Newton's law has given us two equations for 2 dimensions. We can sum all of our forces in the x direction, which in this case would be 225 minus the force of friction minus the x component of my weight, right, as equal to my mass times acceleration in the x direction. And in the y direction, we can do the same thing, right? We can say n minus the y component of my weight is equal to mass times acceleration in the y. Okay. So we can use this to build our equations, right? And it's a handy reference for us because we will automatically, hopefully, be able to see what we have going on. Okay, so I want you guys, this is for participation this week. Right? I want you guys to draw the free body diagram and kinetic diagram for this. I'll give you, let's do 15 minutes, right? You get 15 minutes, draw this up. So a free body diagram and a kinetic diagram for block A. For block A. Couple more minutes, guys. Couple more minutes. All right. Is everybody all right? Anybody want another couple minutes? No? Anybody want to volunteer to show their free body diagram for block A? All right. Well, no, nobody wants to. Nobody wants to. All right. Well, let's see. We've got here 1, 2, 3. So it looks like we've got like a 1 in 6 chance, right? You guys, it's basically a roll of the dice here. Man, this is exciting. All right. How are we gonna do this? Okay. And I'm thinking of a number between 1 and 6. Everybody put a number between 1 and 6 in the chat. Man. You guys all picked 2, huh? I picked 5. And since Zach is the closest, Zach can pick who gets to do their free body diagram for everybody.
Okay. I was considering going. It's just, man, it's hard to see.
I mean, you can pick yourself. You can pick
Okay.
somebody else. You don't have to pick yourself. I'm giving you the power to choose, Zach.
Okay.
Up to you. See, this works both ways. So I get somebody to do it, and also people aren't mad at me now because you're the one that picked.
I don't know. I guess I nominate Brandon.
Brandon.
Oh, he deferred to me.
Yep.
Hmm.
Hold on. Let's see this. You're gonna have to turn your background off so that we can see what you got.
Yes. 1 second.
Guys, just think about how much easier this will be next week, right? And just be happy about that.
So happy about that.
1 second. I'm trying to figure out how to turn it off.
Go to where your video is, right? Pick the up caret. Go to choose virtual background. Your first choice in that menu should say none. Click on that and then you should be good.
Yep.
There you go. Can you put that up there one more time?
Oh, it was literally nothing. I don't know if you got my individual form. I was driving all day and I literally just got
Okay.
here. So I started drawing my free body diagram and it was not very
Okay. No worries then. All right. Does anybody else want to show what they did?
I can show mine.
All right, cool. Thank you, Alexis.
I don't know what it's gonna be like.
All right, so we've got a normal force from the block sitting on the top. We've got the normal force from the ground, right? You got friction. You've got the weight. You got all the tensions. Yeah, that looks pretty good. There's one thing you're missing, but that's okay. It's okay. It looks good otherwise. Awesome. Thank you. So let's talk about it, right? Let's see. So the one thing you were missing, Alexis, was the friction between the block on the top and this friction right here, right? This green friction that I have here, right? That was it. Okay. Otherwise, good. And remember, these things are equal, right? So what do we have, right? When we remove this from everything, so why do we have to deal with that friction? Well, that friction represents an internal force, right? Think about it this way. If the block is going to be moving on the block and the block B and the block A are moving relative to one another, right? They're sliding against each other, right? And so if they're sliding against each other, there's going to be some friction there. Another way of thinking about this is if that wasn't a block that could move, right? If this was to fit in a wedge, right? Like if this was the wall up here, right? The wall would generate friction against that, right? Because it's touching. So there's still some friction there. Now we're going to notice that when we actually start doing problems, for the most part, we're going to have this nice clause in there that says neglect friction, right? So we can ignore it for a large portion of problems, but we're not there yet, right? So cool. That's free body diagrams, right? Remember, we need this tension here, right? If we don't have this tension, right, that's essential because that is describing how we are connecting back to the wall, right? Okay. Remember, always put your dimensions in there too, right? So the angles are really important. The angles are going to be really important when we start crunching some numbers, which is going to happen right now. Right, so let's try one of these, right? We'll try this one together, okay? So look, I've got a 200-pound Pez, right? I've got a 200-pound Pez here. It seems a bit excessive to me, but I mean, some people really like Pez, you know? Who am I to judge? So a 200-pound Pez rests on the horizontal plane. We need to find the magnitude of our force, right? So we're told we need to find the magnitude. So we don't really care about the direction so much. We just need to find how much of it there is. That's when they're asking for magnitude, they're asking for an amount. When you're asked in certain cases to find forces, you need to give them the vector, right? So we need the magnitude of the force P required to give the block an acceleration of 10 feet per second squared to the right. The coefficient of kinetic friction between the block and the plane is mu sub k is equal to 0.25. Okay. So we can't neglect friction. How do we know we can't neglect friction? Because we're told what the frictional coefficient is. Let's just to refresh, right? The coefficient of static friction defines the maximum amount of friction that you have in a system, right? It means you're not moving and you need to push with a certain amount of force to overcome friction. What is that force? It's the normal force times mu sub s, right? After we start to move, our coefficient of kinetic friction takes over, which actually lowers the amount of friction that we have in our system, okay? 0.25 is a pretty typical value for coefficient of friction. Normally they're between 0.2 and 0.3. Certain things have higher, some have lower, right? Like Teflon has a low coefficient of friction because it's a non-stick surface, whereas things like Kapton from Kapton tape has a very high coefficient of friction. All right, so how do we do this? Well, if you believe me, right? If you believe me. All right, so let's start this way. Let's start this way. What kind of problem are we being asked to solve, right? We are being asked to find a force. If we're being asked to find a force and we're given an acceleration, we're going to probably be dealing with a Newton's second law problem. The other thing is we haven't talked about how to do any other kinds of problems, right? We were only the whole topic is Newton's second law. So this is going to be an F equals ma problem, right? So what are we being asked to find here, right? What are we being asked to find? We want the magnitude of P when A is equal to 10 feet per second squared. That's what we want. So the first step is going to be drawing our free body and our kinetic diagram. That's the first step. So what does my free body diagram look like for this, right? Well, I have my pes. I've got my force here. That was my force P. We were told that P is at 30 degrees. I have my weight acting at the center of gravity, right? This is 200 pounds. That's my weight. I've got some normal force, and I've got some friction here. Call that little f. Friction should always act opposite the direction of motion, right? It's always going to be fighting us. I'll draw my coordinate system here. I'm going to use this XY coordinate system like so. And then let's come over here and draw our kinetic diagram, which has M, A in the X direction and M, A in the Y direction. Let's talk about this for a second. What's my acceleration in the Y direction for this problem? So if I was pushing this block, which direction does it want to move? Does it want to move? So which direction would you assume that it wants to move? Gut feeling, right? Gut feeling.
Right.
To the right,
I
right?
think the
Along,
y would be 0.
right? So unless there's a sick jump that we've put here, right? I see no reason why we would accelerate in the Y direction, right? If we're pushing on this, right, and we're pushing down, right? We're pushing down and to the right. This should move to the right because, so there's a couple things, right? So first off, unless you're the Incredible Hulk and you're really pushing on this thing with a massive amount of force to create a crater into the ground should do a pretty good job of resisting you pushing, right? The second thing is it's pointed down, not up. If it was pointed up, then yeah, we'd have to talk about maybe some acceleration in the Y, but we're going to say that this is 0. And we know what a sub x is, right? Because this is going to be a sub x, 10 feet per second squared. Right? So what equations do we have here, right? What's my equations? Well, right now, the only equation we have in our toolbox when it's concerning kinetics is the sum of the forces. In this case, I'm going to say the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. Okay. So what forces do I have in the x direction?
friction force.
Looking at
and
my
the
free
X
body
component.
diagram, what do I have in the X direction?
X component of the magnitude P, or of the force P.
So what do I have in the X direction, guys? What are my X direction forces? Look at the free body diagram. What's acting in the X direction?
Would you have to like use sine rules to find what P is doing in the X direction?
Yeah. Right, so there's an X component of P for sure, right? So for right now, why don't we just call that P sub X? What about, is there anything else?
Friction.
Friction, right?
Is
Notice
my
my
mic working?
signs. P sub X, the X component of P is moving to the right, right? Friction is moving to the left. According to my coordinate system, right here, right? X is positive to the right and up. So since this force is moving to the left, since it's moving to the left, it's negative. All right, cool. And this is equal to what? Well, that's equal to my mass times my acceleration in the X direction. Okay, so let's talk about this. How do I break down this X direction, right? Well, is that going to be a cosine or a sine? If I drew this out in terms of my components here, right? This is Py over here, and this is Px. Is Px going to be sine or cosine of 30 degrees? We'll draw it over here. That's P1.
It should be cosine.
Cosine, exactly. Exactly, right? So we're left with P cosine of 30. Right? We talked about this earlier. This is mu sub k times n, right? And that whole thing is equal to my mass times my acceleration in the x direction. And I'm going to stop there, and I'm going to call this equation 1 for right now. We're going to come back to it in a second. I'm going to come back to it in a second. I'm going to need another slide, though. That's what I'm going to need. All right, so that's in the x direction, right? Okay. So we got to do the same thing in the y direction. Why? Why do we? Right? You said that it's equal to 0. So doesn't that mean that it's negligible? No. And here's why. Look what happened in this equation. I know the acceleration in the x direction. I can figure out the mass because I have the weight. I know mu sub k, but I don't know p and I don't know n. That's two unknowns, right? Two unknowns. How many equations do I need to solve for two unknowns? Two equations. So let's plug, what's the other equation I have? It's the sum of the forces in the y, right? So this should just be Py plus n is equal to 0, right? oh, sorry, minus the weight, right? Dr. D, what are you doing? Minus the weight equal to 0. Okay. Well, if that was cosine 30 for y, that means it's going to be sine 30, right? It's negative because it's pointing downward. And minus 200. Now I've got two equations, right? Now I've got two equations. You guys see where those come from and understand why we're using both? Because I have two unknowns in each of these, right? So I can create a system of equations to solve them. So I can create a system of equations to solve them. Right? So I'm going to rewrite these on the next slide while you guys finish copying them down. All right, so we end up with, we had P cosine of 30 degrees minus mu sub k times n equal to m a x, and we had P, negative P so here are our two equations. Right? These are our two equations, 1 and 2. Let's start with the x direction. We'll plug in the things that we know. All right, we'll plug in the things that we know. So I've got P cosine of 30 degrees minus 0.25 times my normal force is equal to 200 divided by 32.2, right? It's mass divided by, or weight divided by gravity is equal to mass times 10. And in this case, I'll have negative P times the sine of 30 plus n, and I'll set this equal to 200. So there's a couple of ways that we can handle a system of equations, right? You can use your favorite method to solve them, right? One way to do it is, right, I can take this second equation here, solve it for n, plug n back into the other equation, right? So if we call this, if I call this 1.1 and I call this 2.1, right? I can take 2.1, solve it for n, and then throw that into 1.1, right? And do that and solve for p, right? I could do that. You can also do what we call solve the equations simultaneously, right? You can solve them simultaneously. Well, how would you do that? You can use your calculator. A lot of calculators can do them. If you have a TI 83, you can use RREF to solve two equations at once. Right. If you have a TI 89, you can actually implement them. If you use MATLAB, right, you can solve them simultaneously in MATLAB, Wolfram Alpha, all those things. Right, those are all valid solution techniques. The way that I typically do it, I solve them simultaneously in my calculator. That's how I typically tend to do it. Right, but it makes class a little bit less exciting. So, what if we solve this, right? What if we solve this? We'll solve this one here for n, right? N is then equal to what? Well, it's going to be equal to 200 plus, well, sine of 30 is just 1/2. Right, so I just did some algebra, right? I solved this equation 2.1 for n, and I got 200 plus 1/2 p, right? I'm going to take this, and I'm going to put it in here. Okay. So what does that give me? That gives me P cosine of 30 degrees, which I don't know off the top of my head, minus a quarter, right? Because 0.25 is a quarter, times 200 plus 1/2 P is equal to 200 over 32.2 times 10. Now we can solve, right? Remember, we were asked to solve for P, right? How strong is P? Now we just solve for P here, right? do a little legwork and solve for P. Pull out my calculator, the fancy version. Hey, just so you guys know, I don't know if you guys knew this. I learned this late in life, right? But if you're using an iPhone and you open the calculator and then you turn your phone sideways, it gives you all sorts of cosine and sine functions that you can use, just so you know. I know. I'm old, right? So cosine 30 is 0.866, right? And that's in degrees or is that in radians? Man. Yeah,
I think that was 2 degrees. Mine says degrees, and that's what I got.
0.866. All right, so it's 0.866 P is equal to a quarter of, it's not equal to, sorry, minus a quarter of 200, which last time I checked was 50, plus a quarter of a half, which is an eighth of P, is equal to 200 over 32.2 times 10. That should be 62.112-ish. All right, so I'll add 50 to both sides, right? So that'll be me 866 plus 1/8 times P is equal to 112.112, right? You guys see what I did, right? I took this 50 and I added it to the other side. Then I grouped my like terms, right? Because those are both multiplied by P. Well, now I can divide by 1/8, right? Well, let's figure this out. 1/8 plus 0.866 is 0.991, right? 991. So P is 112.112 divided by 0.991. Oh, that doesn't come out right. That does not agree with the answer that I have written in my notes. That's what I get for not bringing my calculator to class, guys. I'm using my phone. Just phone is inferior to any actual calculator, whether it's graphing or otherwise. Just throw that one out there. What are you guys getting? I messed something up somewhere.
Are all the units consistent?
Oh, I see what happened, guys. I see what happened. This should be minus. It should be minus. Right? That's the issue. That'll do it. Sign error. That's negative, right? Because this is a negative a quarter times 200 and a negative 1/4 times a half. Right? So we get 0.866, right? So cosine of 30 minus an eighth. This should be 0.741. Okay. There it is. 151.3 pounds. Okay. There it is. Okay. Apologize for the sign error, guys. My bad. Dr. D loses half a point for today's class. Puts me in the negative. I'm not entirely happy about that. What if you were asked to solve for n? How would you get n now? Well, you take that p-value, right, that we got. We could take this and we could plug it in to this equation here, right? And you could figure out what n is. And so it'd be 200 plus 1/2 of 151.3. Okay. Aside from the sign error, are you guys following how to do this, right? For a two-dimensional, all right, so for two-dimensional problems, right, we have two equations that we can work with right now. We have some of the forces in the x direction and some of the forces in the y direction. What does this mean? This means that the most that I can ask you to find in 2 dimensions is two things, right? You can only have two unknowns in 2 dimensions, right? You only have two unknowns in 2 dimensions for particles. Okay.
If I may ask, I guess I'm a little confused in how a force in the x direction, like in the beginning, max is equal to 200 over 32.2 times 10.
Gotcha.
I mean, I'm guessing the 32.2 is the gravity, but
Yes. So remember, Zach. All right, let's go back to our free body diagram, right? So back here. We're told that this is 200 pounds, right? 200 pounds is the weight. It's how much it weighs. What is weight? Weight is mass times gravity. But I need the mass, right? So mass is the weight divided by gravity, right? Which in our case is 200 divided by 32.2. All right, does that clear that up? I didn't
yeah, and
explicitly
then
state
what was
the
the 10
mass
for?
What's
Or,
that?
oh, I get it. Never mind. I gotcha. Okay, I see.
Yeah. So remember, I don't expect you guys to memorize a bunch of stuff, but there's two quantities that you really do need to know, and that's what gravity is in English and what gravity is in SI, right? That's so, and don't mix those up, because you'll be very sad if you mix those up, because the answer will be shockingly wrong. Good question. Yeah, I didn't explicitly say what the mass was. So how are you supposed to know, right? How are you supposed to know? Because in customary or English units, we use pounds for force and we use pounds for mass, right? So how are you supposed to know, right? Are you just, you guess and you pray that you got it right, right? No. The general rule of thumb is if you are told pounds by itself, that is a weight. If you are told pounds mass, that will be a mass. So typically we make the distinction between pound force and pound mass, right? If you see pound by itself, assume that it's pounds force. Also 200 pounds as a mass, right? Think about this too. 200 pounds, if that were a mass, how much would that have to weigh? That would be 600-pound block, right? So that seems a bit excessive, right? It seems a bit excessive. So general rule of thumb, if you're given something in pounds, assume that it's force unless you're told otherwise, okay? Okay. Any other questions? Any other questions? You all right? All right. Well then, I got you guys something. So I want you guys to take like 30-ish minutes, work on this problem. If you want, I can put you in your groups. Let's see how many. We've got 7 people or 6 people. I mean, I did breakout rooms. We did 3 and 3. We could do it. Let's do it in breakout rooms. Hey, it randomly assigned you guys to these breakout rooms. So that'll be fine. All right. So you guys working in your groups. And I will bounce back and forth and ask, make sure you guys don't have any questions. We'll do 30 minutes. Sound good? All right. I'll give you guys a couple seconds to write down the problem. You guys get 30 minutes. I'll bounce around. If you guys don't know where to start, remember, start with a free body diagram. They are in breakout rooms. If you're watching this because you're not in class today, that's fine. Please pause the video, right? Pause the video and see if you can do the problem too. All right? Take as much time as you need. Try to keep it to 30 minutes. Okay, time to jump back in. There's a poll. Who set up?
Yes, there is.
That's crazy. All right, so you guys were on the right track for sure. All right, and it's I will say this right now, right? So a lot of this stuff is gonna feel like repeat physics 1 stuff for the moment, right? We're not gonna tackle anything like earth shattering for a little bit. All right. Cool. Is everybody back? Yeah. We lost somebody. Somebody bolted as soon as those breakout rooms went up. Don't think I didn't notice. You know who you are. You're probably not watching this video though, so it doesn't really matter. All right, cool. Excellent. I mean, that's true. I get that you don't understand the question, right? Are any of us really here? How do we know that we're here? Right? It's tricky. It's tricky. I mean, I've been telling the other faculty members for years, right? For years, that I'm convinced that this is all this entire thing is a figment of my imagination. I'm just creating you guys as I go. You know, that's. But anyway, I'll stop being weird for a second, and we'll go over the problem. How about that? Deal. So what do? We draw our free body diagrams, right? We're gonna draw our free body diagrams. And I'll draw the free body diagram for it. Remember, if you don't know where to start, make sure you start with a free body diagram, okay? If you don't know what to do, do something. That something is free body diagram. So here's my free body diagram. What do? Well, I have a normal force from the block sitting on top of A. I've got a normal force from the block A sitting on the ground. And I've got the weight. And those are all of my forces. And that's going to be my mass equal to my kinetic diagram, my mass times my acceleration in the X and in the Y. In the Y, we're going to say that's 0 for the same reason that we did in the last problem, except that this time it's much less interesting because we don't have friction. So we don't have any reason to investigate it for A, and that's fine. You'll notice for B, for block B, I tilted my axes, and I call these X prime and Y prime. Do you need to do it that way? No, you can use the same axes. It actually makes the problem a little bit easier if you don't tilt your axes, kind of. But in this case, I tilted my axes, right? Why? To show you that you can do that. It's fine. Both halves of this problem do not have to be talked about with the same coordinate system. You can use whichever one you want. Now, there will be a consequence to this when we get to the next part. But for right now, this is good. And you can see here, right, like right here in this next to my KD, right? All right, so what are the forces? We've got the weight of B and the normal force. That's it for B. And that's equal to my inertial terms in my KD, right? And you can see next to that diagram, I've got 2 sets of coordinate systems. I've got X and Y and X prime and Y prime. And I've drawn them there like that. You don't need to do that, but I've drawn them there so that you guys can see, right, that these are offset by 30 degrees, right? That'll be important later. What was I asked to find? That's to find the acceleration of A and the acceleration of B with respect to A. And what do I know? Well, I know that the weight of B is 12 pounds, and I know that the weight of A is 30 pounds. Okay, so where do we go? Well, let's write some equations. Let's write the equations for block A. Right, and for block A, like I said, we're going to sum the forces for A in the X direction. And that's going to be the mass of A times the acceleration of A in the X direction. Right, so I'll plug in some things. What do I have in the X direction? Well, I'll have N sub B times the sine of 30 degrees is equal to mass of A times A sub A in the X direction. I'm calling that equation 1. Right, and right now, I don't know A sub A. or n sub b. So I need at least one more equation to figure out what is a sub a, right? And that's a sub a in the x direction. That is a sub a, right? There's no acceleration in the y direction, right? If we need to remember it, we can always write that this is 0 right there, right? All right, so that's interesting because I don't know this and I don't know this. So how am I going to get n sub b? Well, I can start writing equations for block B, right? I'm going to do that on the next slide. I'm going to write my equations for block B on this slide. Right? And so for block B, I can sum my forces. Let's make that look better. Sum my forces in the x prime direction or in the x direction, if that makes you more comfortable, right? In the B, MB, AB, x prime, right? And what does this equal? Right? The sum of my forces is just negative weight times the sine of 30 degrees, right? Because I tilted it. Is equal to the mass of B times AB x prime. I'm going to call this equation 2, but notice what happened here. Now I've got this. I don't know that, but I know everything else in that equation, don't I? I know the weight of B, and I know the mass of B, right? So I should be able to solve directly for AB x prime. We'll come back to that in a sec, because our third equation is going to be our sum of the forces in the y direction.
I'm still confused about using pounds for weight and mass.
I'm sorry, Julian, what was that?
I said I'm still confused about using pounds for weight and mass. Like I didn't know which one was which in this.
Gotcha. So remember, if you're just told, right, so let's go back to the problem statement, right? Because that is a sticking point, right? We need to, so the general rule of thumb is if you're told that something is 30 pounds, that is a weight, right? If you're not told if it's pounds force or pounds mass, always treat it as a force, okay? If you're told that something has 30 pounds mass, then use it as a mass. Another way of thinking about this is, right, if that was the mass, if 30 pounds was the mass here, that would mean what? That would mean we'd roughly be 1,000-pound block, right? Which seems a little bit, I mean, it's not impossible, right? But it seems unwieldy, right? So for something like this, it might not seem obvious what the weight is supposed to be, right? 900 pound, like this is a made up thing, right? We don't have this. But if we start talking about like a car, right? And they tell you something has, is 1,000-pound car, right? That's probably not, that's not the mass, right? That would be a ridiculous thing to think about for the weight. So the general rule of thumb is if you're told 30 pounds, assume it's the weight, not the mass, okay? And the only time that you're ever supposed to use it as a mass is when you are explicitly told that it is pounds mass, okay? So let's go back to our y direction equation for block B. Remember, I'm using that tilted coordinate system, right? And so I want you to take a look at my free body diagram again, because I'm using the tilted coordinate system. This is nice because I only have NB in the y direction, right? I still have to account for my weight in the y direction, but I can solve directly for that normal force, okay? As we'll see in a second. Right, so the normal force, this sum of my forces is the normal force minus my weight, cosine of 30 degrees. And this is equal to 0 because I'm saying that in the y prime direction, this should not be lifting off of my surface. Again, right, because of the way I've drawn my coordinate system, right, this is not lifting off. This is going to be 0. So this is going to be 0. If you wanted to use x and y, you could, right? But Now your acceleration, right? Now your acceleration would be describing this green arrow, right? These green arrows. And that has X and Y components, right? That has components along the axis. So the Y prime, the Y direction in this case is not 0, right? The Y direction for the green arrow, that's not a 0 acceleration. You have to figure that one out. So that's one of the benefits of doing the blue coordinate system. Where's my mouse? There it is. All right. Come on. All right. So there's this. I'm going to call this 3. Right? And look, here's that. I can solve directly for my normal force now, right? So I've got 3 equations and 3 unknowns. We're good to go, right? We just plug and chug. So if I solve this equation, right, for n sub b, I'll find that NB is equal to 12 cosine of 30 degrees, right? Which is just NB is equal to 10.39 pounds. I can plug that back into the equation for block A, right? So I'll plug that back in, and I'll get 10.39 times the sine of 30 degrees is equal to 30 divided by 32.2, right? That's the mass of block A, the mass of block A, times A sub A x. Okay. Well, I can solve this for A sub x, and I'll get 5.58 feet per second squared. Part A done, right? So not too bad. We just had to figure out what the normal force is and plug that back in. All right, so I did that kind of fast, right? So what equation did we use for this, right? Come back here. We're using this. We're using this equation 1 right down here. I'm plugging in what I've solved for my normal force, right? Plugging in what I've solved for my normal force. Okay. Again, right? Again, could you solve this in the y direction, or in the, if I used if I use this as my coordinate system, can I solve this? Sure you could, right? You know what the weight is, right? The weight doesn't have an x component there, you just have the normal component. But the problem is you need to solve a system of 3 equations simultaneously to get your answers there, right? Because you don't know what a b sub y is in that case, okay? So you're going to have to solve a system of 3 equations. It's not impossible, but it's a little bit more time consuming. Okay, so here's a sub x, right? So what's the next part, right? Well, the next part is I need to find AB with respect to A, which is just A sub B in the x direction minus A sub A in the x direction. Where does that come from? Well, it's the relative acceleration equation we talked about last week. So how do we figure this out? Well, how do I can figure out ABX prime from the, so let's solve this equation right here. We're going to solve this one, right? We're going to find ABX prime, okay? So ABX prime is just the weight, which is, it's negative the weight. So the weight of B was 12, negative 12 sine 30 degrees, right? Divided by the mass. Well, the mass is 12 over 32.2. So this is going to be negative 16.1 feet per second squared. That's negative. So what is this telling us? This is telling us that that is moving to the left, right? So it's moving down the slope, which is what you would expect if there's no friction, right? You're moving the block in one direction and this is accelerating down the slope. It makes sense. It makes sense. But how do we get this in terms of this coordinate system, right? Because remember what's going on here. I'm gonna need another slide. Give me one sec. I'm gonna do one more slide. All right, so I want you guys to remember what's going on here, right? Remember, I'll draw this like this. This is why I drew this on the other slide. I know you can't see what I'm doing yet. It's fine. This is the coordinate system for the block B, right? Here it is. And look, I'm going to draw my acceleration. My acceleration in this x prime direction is ABX prime, and it's negative, right? It's negative. This is my actual x direction, and this is 30 degrees off of here, right? So in order for me to add, that's x, in order for me to add up this, so that means that this angle in here is also 32 degrees, right? Because they're complementary angles. In order for me to add ABX prime and x, right, in the x direction, what do I have to do? Well, I have to take the component here, right? And this component, this is ABX. How do I get ABX? Well, ABX, A sub B in the x direction, is what? Well, it's ABX prime cosine of 30 degrees. So this is like, because of the way that I've chosen my coordinate systems, I've now had to do a double trig thing, right? But I didn't have to solve 3 equations simultaneously. I know all these things, right? So this is negative 16.1 times the cosine of 30 degrees, which gives me negative 13.94. So A sub B with respect to A, as we wrote before, is AB minus AA, right? Which is negative 13.94 minus 5.58, because I solved for this earlier. Right? Solved for both of those. So A sub B with respect to A is negative 19.52 feet per second squared. You guys have any questions on this one? That last part, right, probably is confusing, right? It's probably confusing. As I said, you could have done everything in the other coordinate system, okay? I don't have that worked out with me right now, and it's going to take more than 10 minutes to do. So, you guys have any questions? I'll work it out the other way for you guys, and we can talk about it at the beginning of next class using the not rotated coordinate system. Okay, maybe that'll help.
Yeah, we used, I mean, at least I did. I used a totally different way and was wrong. I don't really know how to use the other way. Wait, so can you go back to the first equation for how to solve for A, or like the acceleration of A?
Yeah, right here.
Yeah, so like where do you know where to start, I guess? I mean,
So really what you're going to do, right, is you're going to write down all your equations, Julian, right? So for block A, I have my sum of the forces in the x direction, right? Now, if, we'll try to do this quick now. Here, give me 1 second. I'm gonna put it in another slide and we're gonna try this. Okay. We're gonna try to do this on the fly. I don't know if this is wise or not, but we'll do it quick. All right, so if we did this, forget rotating this, right? We're gonna use X and Y, right? Here we are. So I've got MB, AB, X, and MB, AB, Y, right? Okay. So now I need to come up, my equation for block A doesn't change, right? Everybody's cool with that, right? So now I need to know, but I still need this normal force in order to find A sub A, right? Okay, cool. So let's go and let's write some equations for B, right? If I can get this to work. There we go. Is that it? There we go. So if I'm going to sum my forces, right? This is block B. I'm going to sum my forces for B in the X direction, right? What did I have in the X direction? Let's go back. Well, in the X direction, I now have right, where this angle in here is 30 degrees. Well, I'm going to have negative NB sine 30, right? That's clearly it's going negative there. So this is negative NB sine 30. Makes sense, right? Because it's an internal force, so that should be equal and opposite. So this is negative NB sine of 30 degrees. The weight doesn't have any X direction, right? The weight's acting purely in the Y direction, right? So this is equal to the mass of B times the A sub B in the X. And this is what we're going to call, we'll call it 2 prime, because this is the second way, the other way of doing this, right? I also need to sum my forces in the Y. Well, in that case, what? I've got NB cosine of 30 degrees minus the weight is equal to the mass of B times the acceleration of B in the Y direction. In this case, I can't call this 0, okay? Because I'm on an incline, right? So check this out, right? I'm on an incline. If I start here and I slide down to here, right? I've changed my Y position, right?
Yeah.
So there is some acceleration in the Y here. So you can't assume that that's 0, right? So what do we have? How many unknowns? This is unknown, this is unknown, this is unknown. That's going to be problematic, right? Because now I've got 4, but I've got 3 equations, right? So how am I going to do that? Well, technically you're good, right? Because you have this equation, AB in the X direction is equal to AB, in this case should be sine of 30. Well, I have to double check that. Hold on. So you're gonna have to use trig identities to get these two in terms of each other, right? So if we're looking here, our actual acceleration, right, we know is in this direction, right? This is, so we have to break this into components, right? So it's 60 degrees in here. In there. Right, so you have to break this into components using this triangle now, right? So this is A sub B. A sub B is what? A sub B in the X is A sub B times sine of 60 degrees. And AB Y is equal to AB cosine of 60 degrees. So now you can plug these back into these two equations and you've got 3 unknowns, right? You can solve for A sub B, you can solve for NB, and you can solve for AA. Okay. So what do these become, right? We'll write this one in red and we'll write this one in blue, right? The red one now becomes NB negative NB sine 30 degrees is equal to the mass of B times the acceleration of B sine of 60 degrees. And the y direction, let's see, this is B in the x direction, B in the y direction becomes NB cosine of 30 degrees minus the weight is equal to the mass of B times A B cosine 60 degrees. And that's what we end up with. So those are our three equations. We have our three unknowns. We have to solve all of those simultaneously. And then we're good. All right. You know what though? Since we've got 4 minutes left in class, I'm going to say you guys take those three equations, right? You're going to take these three. I'll write the other one down also, right? A sub x. I want you to take these three equations. NB sine 30 MA x. NB sine 30 degrees MA A sub x. Right? I want you to take these three. And for participation, right? Extra participation points, right? I want you to work these out and figure and check to see that A sub x equals what we got in from the other way that we solved it. Okay. Just double check it. Okay. When you do that, send me a private message. Right. So part of the participation points this week will be proving that you get the answer that we got doing it the other way. Okay.
What was the answer again?
Oh. I suppose I can show you. I suppose. So the answer for A sub A, we're not worried about the relative one right now. Let's just worry about, does this come out the same? So you should get 5.58 feet per second squared. What you should get. Should come out to that. And we know what NB should come out as too. So actually all of the answers, right? Basically, you can figure out everything. All right. All right.
So what are we trying to actually prove then?
I want you to solve those three equations, right? It's good system of equation solving preparation. So I want you to solve those three equations that I have boxed on this slide. Wait for it. I'll get there. I can't go too fast or it ruins all the slides, guys. I apologize. All right, so I want you to solve all these three equations and figure out what A sub B is, A sub X, and the normal force. And compare that to what we found doing the problem the other way with rotating the axes. Because your answer should come out the same, right? You should get the same A sub B, the same A sub X, and the same normal force. Okay. All right, guys. That is all that I have because it's 3 o'clock and I can get in serious trouble with the police if I keep you longer than 3, right? So there you go. Remember, you can always go back and watch these videos. They're on YouTube at the YouTube playlist that I sent you a link to at the beginning of the semester in the announcements, right? So you can always go back and watch these videos anytime you want. Okay. We're done. Please fill this out. And then if you're moving in the rest of the week, have fun moving in. I'll see you guys again on Friday. And then next week in person. Solid. All right.
All right. See you later, Professor.
Take it easy.
Have a great day, Professor.
Thanks. Take it easy, Bryn. Drive safe. You didn't get back here yet.
Oh, that's the thing. I was driving for the first part of the class. That's
Sure.
why I was on a actual
Not a
call.
problem. Not a problem.
Oh, okay, awesome. I just wanted to make sure that you knew that.
No,
Thank you.
Like, thank you for telling me. I appreciate that everybody's got to get back to campus, right? So, just be safe, right?
Will do. Thank you.
All right, cool.
Good day, Professor.